I'm Jerry Dobson, President Emeritus of the American Geographical Society. I want to introduce my co-authors, Giorgio Spada, Professor of Physics at the University of Bologna, and Gaia Galassi, Postdoctoral Fellow at the University of Urbino, Carlo Bo. We're going to speak today about Aquaterra and the first stepping stones to America. We'll begin with Aquaterra as a global feature, primarily from an article we published in the Geographical Review in 2014. Then we'll shift to global choke points in Aquaterra, our most recent article, which focuses on travel, transport, and trade at the last glacial maximum, the time when sea level was lowest and glaciers were at their greatest extent. And finally, we'll show you our new findings in the Bering Sea, an archipelago never known before that existed from 30,000 years ago to 8,000 years ago. This graph shows sea level over the past 140,000 years. I want to point out a few dramatic things about it. First, that the only time sea level has been as high as it is today are today and 120,000 years ago when the first modern humans appeared. And if you look at the peaks of sea level over that time, there was an uninterrupted period of 105,000 years when sea level was 25 meters lower than it is today. For 59,000 years, it was 68 meters deeper than today. And for 35,000 years, it was 85 meters lower than today. If you go down to 100 meters, it was at that depth 12,000 years, twice the time span of all recorded history. And all of those ended in the last 20,000 years, about 10,000 years ago. So that is Earth's greatest scientific clue regarding its human origins, evolution, and cultural development. We can even see hints of the origins of warfare, for instance. If people are constantly having to fight for new territory to replace what's being taken, or they're attracted to new territory because it's first appearing as sea level falls, it forces them to fight one another. And that must surely had an impact on our later cultural tendencies. In fact, it may be hinting at adaptability itself. If people are constantly changing from smaller and larger spaces, from cold to hot temperatures, from having to move around globally, that could explain why we are such an adaptable species. We've spoken of Aquaterra until 2014. Most people thought of it as regional portions. Here's all of Aquaterra. Beringia was known. Most people knew Beringia. Doggerland in the North Sea, Sundaland, Sahul, those were known. I suggested naming the entire feature Aquaterra to indicate that it is a global feature and that it is sometimes land and sometimes water. It is equivalent in size to South America. It is entirely flat, entirely coastal, mostly tropical. Hence, it would have been the best place to live during the ice ages. It is a vast global realm that is sometimes land, sometimes water, and sometimes coastal wetland. In the article, I urged scientific recognition of an existing, previously undefined and unnamed global feature. It is a physical feature. It does not need humans to justify its existence. However, it is the ancestral home of humankind. Aquaterra is the geographic equivalent of the Anthropocene. The Anthropocene is a time measure of when humans impact the Earth. Aquaterra is a geographic measure of how far they have affected it, the maximum extent. And I felt I had hit pay dirt with the name when I read this statement by a Danish blogger. The name, just say it out loud, savor the word. Sounds great, doesn't it? Tastes good, alluring, adventurous, puzzling. One can only be curious about what mysteries lie hidden in that name, I thought, when I read about the fascinating concept of Aquaterra. My brother and I, Jeff Dobson and I, felt that Aquaterra was so interesting, so important, so complex, that it needed some explanation in a narrative form. So we wrote 2 novels that would show in the modern book what it takes to find it and understand it. And in the ancient book, it shows people actually living in that ancient time and facing the global catastrophe of sea level rise. Fictional, of course, except it's based on real science. I'm going to turn the mic over to Giorgio to speak about glacial isostatic adjustment. Giorgio?
GIA is a complex phenomenon that involves relative sea level change, absolute sea level change, vertical deformation of the ground, and also horizontal deformation of the ground. In these 4 cartoons, you can see a sort of summary of all these effects, with emphasis in the left side to the sea level variations, and emphasis on the right side to the crustal deformation induced by glacial loading and unloading. So close to the ice sheets, we have the classical phenomenon of post-glacial rebound, but actually GIA is causing regional and global deformations, so that we will have sea level variations even far away from the load. The topography is affected seriously by this process, and in our modeling, our first target indeed is to describe these variations of topography through the whole period since the last glacial maximum. This is a nice view of GIA in which the interactions between the key elements of the systems are described. It is due to Clark et al. 1978. There is a mechanical interaction between the ice sheets and the solid Earth, but also some gravitational attraction, of course. And this also occurs between the ice sheets and the oceans and the solid Earth. In the bottom part of this triangle, we see another kind of interaction in which inertial variations are involved, so that there are also rotational effects of GIA, which will change the sea level by changes in the centrifugal potential. So actually in GIA, Earth, solid Earth, ice, and the oceans are perpetually interacting in the sea level equation, which is a general equation describing this coupled process through surface loading, mutual gravitational attraction, and rotational effects. So in order to solve this triangle, so to mathematically address the problem of the sea level equation, we need at least 4 important pieces of information. The first one is the present-day topography, which is a boundary condition for our modeling. We need to reconstruct the past topography of the Earth by means of the solution of the sea level equation with this constraint that fixes the present-day topography to the eTopo1 model, which is shown in this figure. A second input that we need is a grid useful for the discretization of the sea level equation. And our preferred grid, is due to Tegmark, and borrowed from astrophysics. It is a geodesic grid based on the icosahedron properties, and having the very important property of being equal area and constant resolution.
So another input for the model described the characteristics of the Earth structure, density, viscosity, and rigidity that vary with the depth. There are mechanical differences between layers in inner structure of the Earth that influence the response to ice load or unload at surface. The density is derived by the PREM, Preliminary Reference Earth Model, a one-dimensional model representing the average Earth properties as function of its radius. The same for rigidity. Both density and rigidity in general increase with the depth. Viscosity value, conversely, are higher in the transition between crust and mantle, then fall in the upper mantle and transitory layer, and gradually increase again in the lower mantle. A fundamental part of any GA model is the ice history. Extension and ice thickness of ice masses have changed in the alternation of glacial and interglacial conditions. During glacial period, ice masses reach their maximum extension, gray shade, whereas in interglacial periods they melt to their lower extension, in black in figure. There are different ice chronologies that reconstruct the ice history since the last glacial maximum. In our GA simulation for Aquaterra, we have used Icefree developed by Roger Peltier. For further analysis on paleotopography at specific locations, we have adopted the ice chronologies progressively developed by Carl Lambeck and collaborators at the Australian National University, because it starts at 30,000 years before present. To model the GA component, we have to solve the sea level equation, the linear integral equation that describes the sea level variation associated to the glacial isostatic adjustment. To use SELEN, a sea level equation solver developed by Professor Spada and collaborators and freely available for use. The sea level equation is obtained by imposing mass conservation within the system composed by the solid Earth, the oceans, and the ice sheets, keeping at the same time the sea surface equipotential. The resulting sea level variations are not uniform across the oceans for the effects of gravity and deformation, which are delayed as a consequence of the viscoelastic response of the mantle. The paleotopography is reconstructed using an iterative approach, and the present-day topography is constrained by eTopo1 at 1 arc-minute resolution. In the GA runs, an icosahedron-based equal area grid with a spacing of about 20 km is employed, and the length of the integration time step is 500 years. The figure represents the paleotopography at the last glacial maximum obtained solving the sea level equation, the global ice thickness distribution, according to the ice chronologist Icefree is also shown. The application of the GA modeling has allowed the recomputation of Aquaterra, the bottom left frame in red. The extent of Aquaterra computed considering the dynamic effects of GIA shows lower values in respect to Aquaterra resulting from the static computation. The total surface of dynamic Aquaterra is 17.2 million of square kilometers, compared with the 22.5 of the static Aquaterra, with a reduction of about 23%. The rate of change, the red dot curve in the left frame, clearly shows how the extent of Aquaterra is strictly correlated to ice dynamics. In fact, the strongest reduction of Aquaterra surface have occurred in correspondence to the so-called meltwater pulse event, acceleration in sea level rise resulting from rapid melting of glaciers that took place at 1411 and 8,000 years before present. The application of GIA models for paleotopography reconstruction has been then applied in other cases than now the Professor Dobson will show.
In geographical review, we asked, what impact might the changing configuration of coast have had on local, regional, and global patterns of transport? We answered by comparing the global choke points of today with those of 20,000 BP during the last glacial maximum. A choke point is defined as a point at which surface transportation routes converge with two major implications. Maritime choke points affect surrounding regions by funneling trade through narrow ocean route throughways. Choke points are vulnerable to control by a dominant nation or coalition of nations. And global choke points hold additional significance in that they channel transport and trade worldwide. Turn to any introductory world regional geography textbook and you'll see a list of preferred global choke points. The Isthmus of Suez will always be on it, the Strait of Gibraltar, the Isthmus of Panama, Strait of Hormuz, Bosporus and Dardanelles, Strait of Malacca. We felt that even though the Bab el-Mandeb at the southern end of the Red Sea is not normally listed, it should be. It's probably overlooked by its larger neighbor to the north at the northern end of the Red Sea. We added the Bering Strait because while today it's very broad, there were times when it disappeared. And the Straits of Sicily and Messina. I'll go through these very quickly now. There isn't enough time to spend much time on any one of them. Here they are in relation to Aquaterra. All global maritime choke points are either isthmuses or straits. There are certain general principles that we could rely on. As sea level falls, most straits become isthmuses. It falls far enough. But some are too deep, and therefore never become an isthmus. For instance, the Strait of Gibraltar never becomes an isthmus. It is too deep for that. It does narrow from 14 kilometers down to 10 kilometers at the last glacial maximum. The Bab el-Mandeb drops from 25 to 5 kilometers, but never completely disappears. Another general principle is that as sea level rises, isthmuses and coastal plains become narrower. The existing isthmuses never disappear because they're too tall for that. They extend above today's sea level. You can look at this and readily see that the Strait of Messina is narrow, the Strait of Sicily is very broad, but they're both very shallow. And if sea level fell deep enough, the Mediterranean would turn into two separate seas. In the past, there were people who believed that it happened. We found that it did not happen. In fact, there is always, a sailor could always find 100-meter depth to pass through the Strait of Sicily. Strait of Messina does close, but Sicily does not. The Strait of Malacca did not exist, 1,000 miles long, and it disappeared to become dry land. When that happens, the detour to go around it is quite long because of more Aquaterra. A trip from Sri Lanka today, if we had to bypass Malacca, would be more than 1.5 times as far from Sri Lanka to Taiwan. The Strait of Hormuz did not exist. In fact, the entire Persian Gulf did not exist. The Bering Strait did not exist, but what we found there is a cluster of islands, the ones that are in the southwest on the 20,000 BP map, outlined in red, scores of islands. And we named that the Bering Transitory Archipelago. The Isthmus of Panama was 2.25 times as wide as it is today. The Isthmus of Suez was 3.5 times as wide as today. And that would have been enough to cause anyone traveling from the Red Sea to the Mediterranean to consider other routes. There are 4 alternatives on the Nile, one from Suakin to Wadi Halfa, which was very popular during the Middle Ages after sea level had risen, and Foul Bay to the first cataract of the Nile, 300 kilometers by land, 1,000 by water. But we know that became a popular route later and should have been popular when sea level was lower. The town of Berenice there might have become the crossroads of antiquity. With sea level low, it would have been the central connection between the Pacific, Indian Ocean, and Red Sea world and the Mediterranean Sea, Atlantic Ocean world. The Bosporus and Dardanelles is a very complex situation. The Sea of Marmara is very deep. It remains as a lake with transshipment points at each end. The distance goes from 350 today down to 300 today down to 350 kilometers by freshwater river with lake. At dry times, it may have been no river, but there might have been an incentive to divert to the Gulf of Saros, which would create a different exit over there. Well, does it matter? How much maritime travel, transport, and long-distance trade existed 20,000 years ago? Were there any boats? Was there any cargo? Was there any transport of cargo by boats? If so, how can ports and settlements be recognized today? We had to deal with all these issues. We satisfied ourselves that it does matter. I'm not suggesting that you trust us just on our word. I'm suggesting that if you are troubled by these questions, please read our geographical review paper, which explains what is known about all these issues. Let's take one of those global choke points and see how important it is in that place. The Bering Strait. Science writer Finn Montaigne recently wrote in Smithsonian, one of the greatest mysteries of our time when humans made the first bold journey to the Americas. The oldest sites in America, at one time, they were Clovis sites identified by fluted points about 13,000 years ago. And about the same time, other scholars discovered an Icefree Corridor that was in the 1930s. And so these became a matched pair. It was believed that the Clovis people were the first to come across, and they did so via the Icefree Corridor. They were a matched pair for 70 years or so. Now, at AGS, we can take some pride in the fact that the very first article ever to raise the name Icefree Corridor was in the Geographical Review in 1935. The problem with Clovis first via the Icefree Corridor was that human sites in the Americas got older and older, and soon were much older than the Icefree Corridor itself. In fact, recently it was announced that there were humans living in a cave in Mexico 26,000 years ago, perhaps even 31 to 33,000 years ago, doubling the amount of time that humans have been in America. So scholars look for other alternatives, and one very popular, I would say the leading theory today, John Erlandson and his colleagues suggested that a coastal route might have been aided tremendously by kelp forest, so that there would have been enough nutrition. That had always been a concern before. So the kelp highway hypothesis is very popular today. This is our animation of where kelp forest can exist. If you look gradually changing over 30,000 years, from a position way out. I'll show you on static maps. 30,000 years ago, the kelp highway would have been far out from today's coast. 20,000 years ago, it would have been pretty much the same area. By 10,000 years ago, it had moved much closer to today's land area. And by 8,000 years ago, it was against the shore, very close to the shore. Another problem was genetic. It turns out that genetic tests have found that North American indigenous people have much different DNA from East Asian indigenous people. If that was a quick passage, they would have had the same DNA when they got here. But the difference implies that it really had to be a very long sojourn, called a standstill, in Beringia. John Hoffaker said, "Where do you put these people where they cannot be exchanging genes with the rest of Northeast Asian population?" The term we use for that is occupants. How long did they occupy over time? In other words, occupants implies a duration. How long did they abide in the same area before moving on across? And that appears to be thousands of years. The word occupants is used by geographers, especially in the term sequent occupants. And if you look in Merriam-Webster today, you'll see the sample sentence comes from the Geographical Review. I want to refresh you for a moment on the landmarks in the Bering Sea. The Cape Navarin in the northwest is the tip of Siberia. It is 1,260 kilometers from there to the first crossing within the Aleutians at Cape Sarachev. And this animation shows how the landform itself has evolved over 30,000 years. Now, I'm sure you noticed that there were a lot of islands out there. At 30,000 years ago, most of the islands are in the western section or the middle section, very few in the eastern section. At 20,500 years ago, the last glacial maximum, you're beginning to see a few islands in the eastern section. By 10,500 years ago, just as the Bering Strait opened up, there are hardly any islands left in the western section. They're all in the middle or east. And then by 8,000 years ago, they've disappeared from there. So we propose a stepping stone hypothesis. Scores of islands were in place at least 30,000 years ago, poised to accept the migrants in the west and move them eastward, then force them to disembark in the east by 8,000 BP. It's like a giant conveyor belt. Migrants would have been trapped on islands long enough to account for the genetic drift in the Beringian standstill. Islands would have provided shelter, haulouts, game. Kelp forest would have provided ample sustenance. Shores would have provided iodine and DHA fatty acids, which are necessary for brain development. So our conclusions, Aquaterra is the key to understanding human geography, especially prehistoric and early historic time periods, populations and distributions, cultural development. In turn, GIA reconstructions are crucial to understanding Aquaterra, and we feel it has served us well in studying choke points, travel, and first crossing to America. Thank you.